All right. On to 5.5 today. 5.5 is going to give us a lot of different types of equations. And we've solved a lot of different types of equations throughout the semester. But these are all going to involve either exponential equations where we have like a variable in the exponent, or we actually have an equation that has log already written in it. So one of the two forms that we've seen a lot over the last couple of sections. What we're going to do here is I'm going to kind of start off with like a real basic log equation, and then we'll kind of look at some different examples of some different ones. We'll use our calculator for some. A lot of it we're going to solve kind of just using some of our algebra skills and some of those kind of things. All right, so first one. When I say solving log equations, it may not be written as a log to begin with, okay? But we know this is a log equation or equation we can use logs with because we have a variable in the exponent. And that's the one thing that we have not seen up to this point is we've solved a lot of equations throughout the semester, but we haven't seen anywhere we've had like a variable up in the exponent. And so in order to be able to solve this, this is not a real basic equation where I can just put it in my calculator and figure out what it's going to be. Because 2 raised to some power does not get us to exactly 40, okay? And so my answer here, my variable, my exponent is going to be around a decimal. And so for a lot of the problems that we do today, we're going to get decimal answers that will round to whatever place value they tell us to round to. Usually the nearest hundredth would probably be pretty common, but it may change up the directions on what we're going to round to. Okay, so for this, I like to use a 3-step process. Okay, the first step, anytime we see a variable in the exponent, the first thing that we're going to do is log it. And just like we do with any other equation, whatever I do to one side, I got to do to the other. So for this one here, I'm going to log both sides. That's step 1. Pretty simple. Just make sure we do it to both sides. Okay, now the second step, I do it for rhyming purposes, and you might have heard this before back in Algebra 2, is frog it. And the reason I do that is just for, like I said, rhyming purposes. The property or rule that we said yesterday is if I have an exponent, I can jump that exponent in front of the log. That was one of the rules that we learned yesterday. So this becomes x log of 2 equals log 40. Now that the variable is out of the exponent, the third step is to solve it. And when we solve it, we always are trying to get x by itself. And so this is x times the log of 2. So to get rid of the log of 2, I'm going to divide by that entire expression. We can't just divide by 2. We can't divide by log, but we're going to divide by the log of 2. And so we're going to put this into our calculator. What you got to be careful of here is that when you put this into your calculator, a lot of your calculators will open up a parenthesis when you type log 40. So you got to make sure that you close that parenthesis off after the 40, so that we only do the log of 40 and then divide it by the log of 2. Okay. And then depending on what place value we round to, if we just round to the nearest hundredth, I think it's about 5.32. Okay. So everybody good with their calculator on that? Yeah.
Why wouldn't you just transform it to like just a 1 log, like where the base is 2 and it's 40, and you could just type in.
You could, and that would basically be the same thing. Yeah. Or like in the past, we probably would have always used this because Now some of the calculators have the log base, but in the past they really didn't. And so you're right, it is the same thing. So that would work as well, because that's essentially saying this. Yeah, so it ends up being the same thing. Okay, on this next one, we have an E, okay? And this is one of those that we have talked about, and this is one of the reasons why we have the two different log problems, or the two different log expressions. Whenever we have an E, then we always want to use the ln rather than the log. And so we're going to use the natural log. So we're going to do ln of e to the t equals the ln of 1,000. So we still log both sides, but instead of using log, we use ln. And I'll show you why that's important or easier here in just a second, because there's going to be something that we're going to see over and over again that's going to be pretty common. Okay, so we logged it. That's our first step. We're going to frog it so that exponent's going to jump in front of the log. And it's been a little bit, but last week we talked about whenever we have the ln of e, the ln of e is really what? If I just wrote the ln of e up here by itself, what is the base of the ln of e? It'd be e. So ln of e base e would really become 1. Okay, so ln of e is always 1. So this whole thing really just becomes 1. So anytime you see ln of e from here on out, and that's kind of the benefit of using ln as opposed to log, then I can essentially just get rid of the ln of e because it's really just 1, which makes this 1t, which really just makes it t. So to put this one into my calculator, all I would have to do is take the ln of 1,000. I have mine rounded to the nearest thousandth. So we just kind of have to pay attention that they're going to ask you to round to different place values, sometimes 10th, 100th, 1000th. So we get about 6.908. Now, you could check your answer. The only bad thing, we always talk about, like in equations, we can check our answer, right? If I take E and raise it to the 6.908, I'm not going to get exactly 1,000 because this is a rounded answer. I'm going to get something really, really close to 1,000, but it's probably not going to be exactly 1,000. Okay, so just realize that like you can still check this, and you should get an answer really, really close to 1,000, but it may not come up exactly 1,000 if you were to check it. Okay. Okay, if I give you one like this, it's kind of similar to the one we did just a second ago, except now we have a number out in front of the E. Okay, so we can still log and frog and solve it, but before we do that, then I want to get rid of the 100. I want to get rid of anything out in front of the exponent, in front of the base. So what I'm going to do here first is I'm going to divide by 100 first. And that gives us 25. Now that we got this in exponential form, you can use a log loop rule. There's a lot of different things that you can do here today. I like to just log and frog and solve it. And when I do that, as you start doing this more and more, what I kind of like to do is combine those two steps into one. Log it and frog it all into one. Okay? So I logged both sides. I went ahead and jumped the exponent over in front just to kind of save some time, save some steps. We now know anytime I kind of compare it to like I squared. Whenever we saw I squared, we knew I squared was always -1, right? Whenever I see the ln of e from here on out, I know that that is 1. So we have 0.08t equals the ln of 25. And then to finish this out, to get t by itself, we're going to divide by 0.08. Okay. Once again, when you put that into your calculator, just make sure parentheses are kind of important here. We close those parentheses off. Because if I do this and then divide it by 8, then your calculator is probably going to divide the 25 by the 8 first before it takes the ln of it. So that's why it's important to close that parenthesis off. Okay. Calculator is going to try to do order of operations, so it's going to do it whatever you tell it to do, essentially. Okay. What do we get for an answer there? I don't have the decimal for that one. ln of 25 divided by 0.08. Anybody have that?
40.235.
Okay. Okay. This next one is going to look a little bit different. I'm just going to try to show you a lot of different types of problems today, because there's going to be a lot of different variations on problems today. Some are going to be written in exponential form, like these are. This next one is going to be written in exponential form, but it's a little bit different in the way it looks. So we have e to the x minus 6e to the negative x equals 1. I kind of compare this to like a quadratic equation. I know it's not a quadratic equation, but I kind of think of it as the same idea. Whenever we had a quadratic equation, we had an x squared, we had an x, and then we had like a constant. And our first step when solving this was always to, because we essentially have 3 different kind of pieces here that we can't combine together. We can't put all of these pieces together. So my first step on something like this, when I have 3 different pieces like this, is we're going to set it equal to 0. So I'm going to have e to the x minus 6e to the negative x minus 1 equals 0. There's nothing here that we can combine together. Okay. I really can't log it, frog it, solve it, because I've got 2 different bases of e's, and I can't combine those bases together. Especially because my exponent is different. If I had like x squared and x squared, we could put those together. But here my exponents are different. So what we're going to do then is we're going to use our calculator to solve this one. Okay? And we're going to kind of do it like what we've done in past. Is if I have an equation that I can put into y equals, then I can put this into my calculator, graph it. And so let's go ahead and do that. Let's put this into your calculator. Let's graph it. For our answer. So it's kind of a shortcut because trying to solve that one algebraically would be pretty tough to do. Okay, and so that's kind of a shortcut that we could do on something like that, where we could still get a solution. All right, some other ones that we're going to see. We're going to see some that have already been written as a log. Okay, so some are going to be in exponential form, some are going to be in log form, and we have to be able to get x by itself, right? Our goal is to solve for x here. So probably the best thing to do here is kind of go back to what we did last week and just remember your log loop rule again. The base is 5. 5 raised to the 4th power equals x. And then look how easy this will be to solve now. All I have to do is take 5 and raise it to the 4th power. And we get 625. That's our answer. Okay. So if I can remember the log loop, that makes that one pretty simple. If I do ln of x equals -2. Okay, this one does not have a base, so what's my base assumed to be? E, okay. Just remember ln is always base e. So once again, it's another log loop situation. E raised to the -2 equals x. Okay, and it's really just another calculator problem here then. I can take e and raise it to the -2 power. And we get like 0.135 for our answer. Okay, we're going to get a lot of decimals on our answers today. Hey, something like this. Because my exponent is over here, okay? Now, there's a couple of different things that you could do here, okay? Probably the easiest one is to kind of do what we did last week. This is really just a change your base formula. I know some of you have the actual base button in your calculator that you could use here. Because x is already by itself, this really could just be a calculator problem, okay? You could do the log loop rule here, but that would be going through. And now I have x as the exponent, and then I'd have to do log of frog to solve it. So it would be easiest probably just to put this into my calculator right from the start, rather than going through all those steps to solve it. Now, if you have the log base button in your calculator, you can use that here. If you don't, then you can simply just take the log of 1/4 divided by the log of the base. Okay, and you get like 0.3 repeating here. Because it's a repeating decimal, then this would be one I would say, let's go ahead and change it to a fraction. Most of the decimals that you're going to have today are not going to be repeating decimals. And so if it's not repeating, then we'll round it. But if it is repeating, then we can simply change it to a fraction, and a fraction would probably be the better way to leave this. That way we don't have to worry about rounding. Okay. We're also going to use some of the different rules that we did yesterday. Okay, and I'm going to show you a couple of examples where we're going to use some of the different properties and rules. We already did the one where we jumped the exponent over in front of the log. That was one of the properties that we did yesterday. Here's another example of using what we did yesterday to kind of help us today. Yesterday we had some expressions where we had multiple logs. And our goal here is to solve for x, right? And so what we really want to do is we want to condense this equation down. We don't want multiple logs in an equation. We want to take it from where we have multiple logs into a single log. And yesterday we talked about the product rule. If I have a plus sign in between my two logs, then what I'm really doing with those two parentheses is multiplying them, okay? And so we're going to rewrite this as log base 2. and we're going to have to multiply. I'm just going to kind of do it over here to the side. X plus 1, bless you, times x minus 1. Okay, and really that's just a FOIL problem. Okay, we're multiplying two binomials together, so we're going to FOIL those two together. And then we got a negative 1x and we got a positive 1x, which makes the x's cancel out, minus 1. And the 3 over there just stays the same. Now that we have the log expression kind of by itself, we got a single log, kind of like we did yesterday, then what we would do is use that log loop rule again. Okay, and that's why kind of knowing all these different things, knowing how to use the log loop, going back and forth, we're going to see that a lot. So we're going to take 2, raise it to the third power, equals x squared minus 1. So we change it from a log equation now into an exponential equation. We know that 2 cubed is really 8. We can put that into our calculator if we don't know what it is already. And our goal here is to get x by itself. That's our ultimate goal, right? Add 1 and I get x squared. And then here's where you got to be kind of careful, okay? If I were to take the square root of both sides, what do I have to put as my answer here? Plus or minus 3. Okay. Now here's the thing you have to kind of also be aware of. I'm saying that both positive and negative 3 work here, okay? So if I go back to my original equation that we started with, and let's say I started with positive 3. 3 plus 1 is 4. 3 minus 1 is 2. So we're saying the log of 4 base 2 plus the log of 2 base 2 equals 3. If we check that, to see if it really does work, then log 4 base 2 is 2, log 2 base 2 is 1, and 2 plus 1 equals 3. So it checks. Okay. If I tried negative 3, if I plug negative 3 in for either one of these, negative 3 plus 1 is negative 2. What happens if I do the log of negative 2 base 2? What happens if I take the log of any negative number, no matter what the base is? Can't do it. Okay. Last week when we talked about taking the log of something, we can never have a negative number in this spot right here. So can I have negative answers? You can, okay? But when I plug it in, it can't make this right here negative. So that's what you got to be careful of. It's okay to have a negative answer, but it's not okay if I plug it in and it gives me a negative when I take the log of something. So we thought plus or minus 3 was our answer, but the negative does not work. So really only x equals 3 would be our answer. Okay. But don't just assume that negative is never going to work, okay? There is a difference between a negative answer and a negative, taking the log of a negative number. And those get a little bit tricky. Okay. This next one. Once again, using some of the rules that we did yesterday. Very similar to the one we did just a second ago. The last one we did had a plus sign in between. This one has a minus sign in between. And so I told you yesterday that was really the focus of yesterday, is kind of learning how to use the properties. So today, that when we start solving it, we can apply those properties and help us to solve an equation. And when I see a minus sign in between two separate logs, what are we going to do with the two expressions? Subtraction tells us we're going to do what? Division. Okay? So we're going to condense this down to a single log. So we're going to go ln, and we're going to divide the two expressions on those two logs. Okay, here's my first question. Is it okay to just knock these x's out right here? No, okay? Because this one is attached to a plus 1, right? That's an entire expression. In order to knock the top and bottom out, they would both have to be the same. If the plus 1 wasn't right here, then I could knock it out, right? But I can't just knock these x's out because they're not the same expression. If it was 2x over x, I could knock it out. But the plus sign attaches the x and the 1 together. Now, here's what you could notice. If I were to, a second ago, then whatever is in this spot has to be equal to whatever's in that spot because there's an ln on both sides, right? We don't have to change this to an exponential equation. So what I'm going to do is I'm essentially just going to get rid of the ln's here. And I'm going to say x plus 1 over x equals 4. I'm just going to set those two spots equal to each other. Now, our goal is to get x by itself. I got an x in the denominator right here. What could I do to get rid of that fraction? Multiply by x. Good. So I'm going to multiply by x on both sides. That gets rid of our fraction. I'm going to subtract x. And then I'm going to get x by itself. So I get x equals 1/3. And that'd be our answer. Okay, I'm going to show you a couple of different ways that you can approach some of these problems, okay? And especially if this number is a power of 4, okay? We're saying 4 to some power gets us to 64. And we know the exponent is x minus 1, okay? So could I log it, frog it, solve it here? I could. I could log both sides. I could move the x minus 1 over in front, and I could go through that whole process. There's nothing wrong with log it, frog it, solve it here, okay? But what I want to show you here is because 4 does get me to 64, I could rewrite this. I could rewrite 64 as a base of 4. And if I wanted to know what 4 to what power gets me to 64, well, we know 4 to the first is 4. We know 4 squared is 16. 4 to the third power gets us to 64. Okay. And the reason I like this a little bit better is because once they have the same base, they're both base 4s now, then my two exponents have to be equal. X minus 1 equals 3. And then all I have to do is add 1, and I get x equals 4. Okay? There's going to be more than one way to approach some of these problems. Kind of like we were talking about earlier, right? Is there a right or a wrong way? Not necessarily. I mean, obviously there would be a wrong way, but there's more than one correct way that you can get there as well. If I logged it, frog to solve it here, then I could move the x minus 1 out in front. I could do the log of 4 equals the log of 64. I could do x minus 1 equals the log of 64 over the log of 4. And it just becomes a little bit more, I think, a lengthy process. I think this one's a little bit cleaner, maybe easier to solve. But you'd have to be able to recognize that 64 is a power of 4, so I can rewrite 64 as a power of 4. And then I can just set my exponents equal to each other. Okay, so just kind of an alternate method, really, other than anything. You can still log and frog solve it if you want to. There's a couple of different ways you could approach some of these. Okay, one last example I'm going to do with you here, and then I'm going to do one off your assignment with you once I give you the assignment, because there's one on the assignment that is a little bit tricky, I think. I think the hardest part to some of these is, where do I start? Okay, and just remembering your log loop is probably the best thing to think about. Okay, if I have a variable in the exponent, log and frog solve it should always work. If I have a log given to me already in my equation, then probably trying to change it to an exponential equation would be the best route. Okay, so knowing how to transfer this log equation into an exponential equation is a really big deal. Okay, and so I mean we've done that 3 or 4 times today already. 2 to the 5th power equals 10 plus 3x. Once I'm here, I have 100% confidence that anybody could solve in here, right? Because 2 to the 5th, we can simply just put that into our calculator, and now it's a 2-step equation that we've solved for years. It's not a real hard problem once we get here. Trying to figure out how we're going to get here is, I think, the hardest part, okay? And so we're going to subtract 10. We're going to divide by 3. And I would just leave my answer like that. Okay. It would give me a repeating decimal, and once again, if it gives me a repeating decimal, I probably would rather you write the answer as a fraction, okay? If it says round it to a decimal, I'm not going to count it wrong if you round it to a decimal, but if it's repeating, then I would say let's write it as a fraction. If it's not repeating, if it's just a big, long, random decimal, then obviously we're going to have to round it, and we can't change it to a fraction because there's not a fraction form. It's an irrational number. Okay, I'm going to put the assignment up here, and then there's one problem on here that I think is kind of tricky, and we're going to talk about that one. So I kind of just tried to go through and pick and choose some different types of problems, things that I think we should know how to do from this section. So you got those first 4, and then on the last group, 31 to 61, we're just going by 5. So 31, 36, 41, 46, and so on. All right, the one that I'm going to do with you, I think, is number 17. So you can put this at the beginning of your assignment if you want to. Okay, a little bit different than some others that we've done. What kind of makes this one a little bit different is, first up, we have an exponent on both sides, right? And so we can't just simply write this as a log equation. If I just had an exponent on one side, log and frog solve it would be pretty straightforward, okay? Now, because I have an e in this problem, then I'm still going to log both sides, and I'm still going to get the variables out of the exponent. I just have 2 different exponents here, and I have variables on both sides. The base is also not the same. If the base was the same, then this problem would be a piece of cake, okay? But one's a base e, one's a base 5. So I'm going to log it first. And then we're going to frog it, just like we've talked about. And we now know ln of e is really 1. And then we get to this point. Okay. And this is where it gets, I think, a little bit tricky. We don't have any plus or minus signs here, right? And we've done all the steps, but now I got a c on both sides. And here's kind of what I compare it to. If I were to write up here, x equals 6x. Just try to compare it to something we've seen before that doesn't have an ln in it. What value would x be in this equation right here? What value can I plug in for x to make this work? Okay, if I plugged in 1, I would put 1 here, but then 6 times 1 would make this 6, so 1 would equal 6. What do you think? 0, right? If I plug in 0 here, I got 0. 6 times 0 is 0, okay? So 0 equals 0. When you have two variables equal to each other like we do here, yeah, we might have a number here, but I don't really care what that number is, right? I could put any number of coefficient here. Really, ln of 5 is essentially a coefficient here because we could multiply it by 2 if we wanted to, and it would be a decimal. But I could put whatever coefficient I want in front of x. But the only thing that's going to make these two equal to each other is putting a 0 in both, right? So here, it kind of looks difficult. We get to this point, how do we solve it? All we got to really understand is that the only thing that makes those two sides equal is c equals 0. Okay. So, kind of looks a little bit tricky, but if you can remember something like that, it makes it a little better. All right, so just lots of different variations today. There's a couple that you can use your graphing calculator for, like that one that we did. The rest of them is just trying to kind of get a feel for what's going on. There is a little bit of the very first problem, number 10. I will give you a little bit of a hint. There is a little bit of factoring involved. So there's a little bit of factoring involved in some of these problems. So on number 10, try to do that one. You would still log it, frog it, solve it, but you're going to get a trinomial that you're going to end up having to factor. So you got DOPS, you've got product and sum, you got some of your factoring methods that could be available to you there. I'll come back to that one here in just a second. If I said the ln of x equals the ln of 3, what would the value of x have to be to make the two sides equal? 3. Yeah, that's it, right? Whatever is in this spot has to be in this spot because both sides have an ln on it. Okay, if I had an ln on one side and not the other, then that would change things completely. But because we have an ln on both sides, whatever's in this spot has to be equal to this spot, right? And so when I go back to the problem we had just